Could you close the door? I have no audio, actually. But let's make sure. Can you guys hear us? Let's make sure you guys can hear us. Did someone on the someone remote just confirm you can hear us? Hello? Hello, hello? Great. Okay. Well, then let's get started. Well, guys, it's been quite a journey. We've done a tour through all of speech technology, and we're ending with the real world, which hopefully it should be what we all aspire to in engineering. So today we're going to just do a bit of an introduction into ML in the real world. And we're going to go through a series of topics that are all related to the actual pains and tribulations that you're going to face using machine learning as an engineering technique and building larger systems that might include a lot of other technology that has nothing to do with machine learning. So we're going to talk about model management and then how you deploy models into production systems. We're going to talk about model performance optimization, so how you make your model more performant, which is actually very important if you're going to run it at scale. We're going to talk about model validation, how you make sure that it actually does what it's supposed to do. Then we're going to talk a bit about reliability and safety. And then finally, how you communicate about your machine learning models to external parties whom maybe are not as technical or not as familiar with machine learning. And then we're going to wrap up our IAP series, and that'll be it. Okay, so introduction. We're going to talk just really briefly about applied science. So what I'm talking about here is, so let's talk about the field of mechanical engineering. Generally, fields of engineering are developed many years after the fundamental science is worked out, right? So Archimedes worked out the theory of simple machines back in the 200s BC, and Principia Mathematica, Newton, didn't work out the theory of classical mechanics until 1687, but we really didn't see an applied field of mechanical engineering until around the Industrial Revolution with mechanized textile machines in maybe the 1760s. And you didn't actually start seeing your first mechanical engineering professional organizations for another 40 to 60 years after that. Similarly, with electromagnetism, we first discovered static electricity with amber and cloth back in the 500s, 600s BC. And we got Maxwell's equations in the 1860s. But really, we didn't start to see electrical engineering as a profession, as a formal field of applying electromagnetism to electronics and radio until around the 1880s through 1920s. Similarly, with computer science, which is interesting because it's the first time where the scientific study is, depending on how you look at it, a field of applied math, or is studying the idea of computers in the abstract, until maybe the development of the difference engine. There are earlier mechanical computers that go back to the abacus. But you didn't really start to get a theory of computer science that was akin to maybe classical mechanics until really the 30s through 70s with the development of computability theory, complexity theory, analysis of algorithms. And really, software engineering is a profession where instead of a mathematician that was hired to manage a computer that only they understood, but really it was a profession in and of its own right, didn't really start to emerge until the 1980s through like the 2000s. It's a very, very new field of engineering applying a relatively new field of science. If we look specifically at deep learning, things look even rougher, right? We might not actually be on the right side of that diagram. We don't really have a rigorous theory of deep learning. We've done a lot of ideas about maybe how you could roughly apply these concepts that we don't fully understand. And there's a very limited maturity as an applied science as a result. And so we are essentially practitioners of a field that doesn't even have its Principia Mathematica yet, which is, as an engineer, something that we should all be terrified of. And so that's what we're going to be talking about today. So first things first, model management. The first topic I want to talk about is data librarianship. I'm not actually sure if that's a word or not, but Your data is the most valuable thing that you have as an ML practitioner. You can make new models, you can invent new models later, but if you lose your data, you don't get your data back. So you need to protect it, you need to care for it. Organize it. You should think about your directory structure. It should be coherent and consistent. It should be optimized for distributed use so that if you have mini computers, like you might do training a large transformer, that it's segmented and keyed in a way that is consistent. You should have rich metadata, including the context under which the data was collected, so that if years later you want to use the data in a new way, you have that context. You need to make sure that you future-proof your schema, because you might want to extend your data set later in ways that you can anticipate and then make your data reusable for future research. And then supplemental documentation. So you should have a description of the collection and labeling process. The labeling process being in particular important, where if there's a human that was instructed how to label it, the instructions for how they labeled it might be very important if you want to later extend the data set or understand your results. And you should also document what the motivation of the data set's creation process was in the first place. What problem were you originally trying to solve? Because that might help future users use the data set in a productive way. And then finally, restrictions on use. If the data is private or is not intended to build models for another purpose, or there's copyright or commercial use restrictions, you should consider that. So I'm going to use as a case study the Harper Valley Bank. This is a bit of self-promotion for Gridspace, but this is our public data set that we use at Stanford for CS224S. And so here we see clearly marked intended purpose. This is on the GitHub, which, by the way, and hopefully if you've done some of the assignments, you're already familiar with this data set. You can see that we put a lot of thought into our directory structure and file identification. There are clear shared keys in between related files. You see a logical structure of the schema, including units and the names of fields, which I hope you all do. Metadata documents that were collected as part of the labeling process, supplemental documentation, and demarcated restrictions of use, which GitHub actually helps us with in that case. Model versioning, also really important. This is from the Gridspace Conversation API, and you can see here we actually are versioning various models, and this is important for our users who maybe are building downstream models or downstream detectors, where if we change our model version, they then maybe have to retrain their models downstream because their features are no longer valid or consistent. In model inventories, so you might build hundreds of different models, and if you're trying to manage those models, manage that software, compared to maybe managing just text-based software in Git, it can be quite complicated because the weights are obfuscated, right? You can't inspect them like source code. The best you can really do is track the date, the performance of the model, and when it was generated. And so, if you look at this is a picture from Hugging Face. If you look at large model inventories, Hugging Face probably being the most well known, it's actually an incredibly hard problem that is not fully solved when you get into especially open source, where no one really does a good job at documenting anything. In our case, we have production models that we are always improving, and there could be regressions, there could be undocumented weaknesses. And so we do our best to, as a production deployment of these models, track the models over time in a repository that has some of the same properties as maybe a Git repository, but actually is appropriate for large files, is appropriate for many different model versions. So yeah, your model shouldn't live in Git. Git's not intended for large files. Your model shouldn't live in your image. So if you're using containers, which we'll talk about in a minute, ideally, if it's a really large file, it's probably more appropriate to store it in some sort of networked machine or cloud file store. Your inventories should be synchronized with the rest of your development process. If you have a new release of software that pairs with a model, you need to have some synchronization mechanism. And if you are a company that is so sophisticated as to have a continuous integration, continuous deployment system, you need to make sure that your model inventories are synchronized with the CI/CD process. You shouldn't have invisible changes to model files. Basically, if you subtly change the weights of your model and then upload a file to a cloud file store, that needs to have some tracking. And if that's not provided by your cloud file store, you have to do it. And that's that doesn't just apply to models. It applies to maybe large assets if you work at a game development company. And so it's actually a relatively complicated problem, and you have to probably do some engineering if you want to do it well. And then finally, we mentioned this a bit earlier, but model versionings to prevent compatibility issues. So if you're a company like Gridspace, where you build models on top of models on top of models, you might change a model upstream and then have to revalidate everything in the rest of your pipeline. And that's a complicated process that adds technical debt that is mostly irreducible. The only real thing you can do is build larger, more monolithic neural networks, which is a good strategy if you have it. Model deployments. Deployment, if you're not familiar, means to bring code that you've written into a real production system. So bring it from your repository or from your CI/CD system into a production server or hosting system. So the most common modern strategy for managing complexity in modern deployments is the use of containerization. I wouldn't say it's ubiquitous, but the old, just traditional, you run your code on your server model is becoming less and less common. And there's a lot of reasons, and there's plenty of material online if you want to learn more about containerization, the most common technology being Docker. But the idea here is, as opposed to a virtual machine where you might have a hypervisor, which is a piece of software that allows you to essentially run multiple operating systems, what you do is you have one kernel running, with several virtualized operating systems. And one of the advantages of containerization, and I don't want to get too much into this topic because there's plenty of other material you can read, is that you can have a very consistent deployment system that's consistent with your development system, right? So if you install 200 apt-get installs and pip install 1,000 libraries and you run a weird flavor of Linux, you can reproduce that in production using containers. You also have a consistent unit that you can scale, which becomes important when you move into the world of orchestration. But before we get to that, that was a copy and paste there. So orchestration is the practice of deploying mini containers that work together. And probably the dominant technology right now is Kubernetes, which is a derivative of Google's Droid system. And the idea here is that you have fundamental units of deployment, which themselves might contain one to several containers. And then you have deployment systems, which are physical hardware or virtual machines that can accept multiple of these units of containers. And the language used in Kubernetes is pods, or a package of one or several containers, and nodes are abstractions of compute that you have available. And so why this is important to a machine learning practitioner, besides the fact that you hopefully are employed by a company that builds production software, or you are trying to build something productionized yourself, is that as you add complexity to your system and you are trying to integrate many services into a larger and larger piece of software, you need to start to manage your resources so that you don't waste compute on a resource that maybe doesn't need that much compute. It allows you to share resources, and it allows you to have a more natural path to scaling, which is the next thing I wanted to talk about. This is a diagram of from control theory, showing the idea that you have some error that you want to rectify through a feedback element. And in general, autoscaling in the deployment world, for instance, if you're operating a Kubernetes cluster, would typically take the form of a service that has some metric, some scalar that can act as that error function. So typically that might be if the system is starting to lag, or it seems to be hitting the size of a queue that you might be targeting. As you approach the limit of what you think your services can execute given the current load, the idea is that you have some control system that scales up or reserves more resources for that service. And autoscaling, again, is a big topic, but generally there's different types of scaling just in Kubernetes. You might want to scale up your amount of compute, what they call node scaling, and you might want to scale up your amount of services, which might be called pod autoscaling if you're scaling up pods, or maybe you're scaling up your containers. You could also swap in services that are able to handle different amounts of load. One key point about autoscaling that I wanted to emphasize is that if you have a bad measurement, if you're not good at measuring performance or how performance degrades as you hit the limits of your compute, then you are not going to be able to build a good control system. This is true about controls in general, but when it comes to autoscaling compute, if you measure something that is only loosely correlated with whether you have sufficient resources, you're either going to under provision and then have performance degradation, or you're going to over provision and you're going to waste money and resources. And so you have to make sure that not only are you measuring your auto scaling parameter wisely and then you're measuring the right thing, but also that that you have the right margins as well, because there's going to be some variance in your load and some variance in your the performance of your service. And so if you have bad measurement and then you're not going to be able to have narrow margins. So I want to talk a little bit about latency. So imagine that you have a task that you need to do on your computer, and you need to do it once a day. So like, let's say you have to check your email once a day, and it takes you an hour to check your email, right? Let's say that it takes 30 minutes for your computer to boot up. And so then the actual task is 30 minutes of booting up plus an hour of real useful work, okay? Now imagine that you get more and more email, right? So now you're getting so much email that you can't go through all your email yourself. So you have to hire someone else to help go through your email, right? And if you now maybe are checking your email 3 times a day, and your assistant is checking their email 4 times a day or whatever, now that warm-up time is starting to become a bigger and bigger percentage of your total labor time throughout the day. And so you can get in the limit from the queuing theory perspective is very dependent on essentially that warm-up time, or that dead wait time in the time it takes for you to do your task. So now instead, imagine you have a microservice. You have a container that is a speech recognition model, or it is an emotion detection model. And it takes 2 minutes to download the model from the internet. And then it takes another 30 seconds to import everything and maybe create some initial data structures in RAM. That dead wait time means that there is going to be a latency before you can start executing that task. Now imagine that the load increases unexpectedly on your system. That means that there is going to be a period where you are under provisioned. So then, as the operator of this production system, you then try to prevent being under provisioned, which means a catastrophic failure in terms of meeting your requirements. And so you begin to over provision. And so you begin to always scale above the needed load, just in case there's a jump in load that you can't anticipate. And so I hope this illustrates that a very critical performance measure for your ability to rapidly meet load, a rapidly changing load, is the dead wait time to get that new compute up and running and performing its duty, rather than dead wait as it warms up. And so when it comes to machine learning models, a large 100 billion parameter model, right? If those are 32-bit floating point, can be a very large file, right? Not to mention, if your container is full of crap and is itself many gigabytes large, and you're pulling that container from a container registry, you could actually have a fairly large amount of time before you can actually have an up and running service that you've auto-scaled in some sort of container orchestration cluster. And so you have to be extremely conscious in the real world of something that you might not even notice working at your workstation, or working on your laptop, or working in your Python notebook, because you've had everything imported for 17 days. And so the concept of dead weight loss is something that you've never even thought about. And I want to go back to my introduction really quick and just remind everyone that because we are not even at the point where deep learning is itself really a fully mature field of science, the few people that are actually practicing it in the real world and building production systems with it are an extreme minority. If you're Googling on the internet how to build, let's say, a search system, or how to sort integers, you're going to find many, many years of discussions about how to optimize that for performance. And in fields like graphics, where most of the applications are always just performance limited and generally are targeting production systems, there's also a lot more sensitivity to performance. But in the world of deep learning, where 99% of people are mostly just doing research or just doing experiments, there's very little thought about things like bloat in the libraries that you use to build your models, or things like the total amount of time it's going to take to download your model weights. container size bloat, I was just kind of alluding to. This, by the way, if you ever see a package that is bloated, a container that's physically bloated, it might mean that it has botulism, which can kill you, so just don't do that. Similarly, this can also kill you. It's actually probably worse because it affects me too if you make that mistake. But if you die from botulism, it's mostly for you. These packages are intended generally for research, and they're built by organizations that operate production systems that themselves have to struggle with these same issues as even the companies that support the development of some of these open source packages themselves are mostly populated by research employees that don't know much about production themselves. And so if you an experiment that you can do is just create an empty Docker file and install Python, or use a flavor that comes with Python, and then pip install PyTorch, TensorFlow, JAX, NumPy, scikit-learn, all these packages, and you're going to have a package that's like 10 plus gigabytes large, which is going to translate to a fairly large amount of time for you to scale up your resource. Not to mention a lot of bloat that is mostly just code that you don't actually need. So we talked about warm-up time. Okay, so, oh, by the way, I guess I should talk really quick about how you deal with this, right? I have some optimization strategies up ahead that partly deal with this, but generally, at the end of the day, deep learning is a bunch of matrix multiplies. And we've been writing software that's really good at matrix multiplies and building hardware that is really good at matrix multiplies for a long time. Most of the software that you see here is other crap that is intended to either help you do research or help you validate models or to bring in data sets. And that stuff is really useful at the research stage, but you probably don't need most of it. But you can inspect your model weights, and you should understand every matrix multiplication and every activation function and every loss function that live in this. And maybe you don't even need your loss function in production because you're not training something, maybe you're just doing inference. And so there's a lot of strategies that you can take to reduce bloat. The easiest is if you just imported pandas so that you could do some sort of little test or do some little thing that you could have written in a 3-line Python function. Ask yourself, do I need this import still when I'm entering production? Or was this just for research and development? And we're going to talk about some other strategies in more detail in a second. So model performance optimization, this is a really big subject, and it's a really interesting subject. And I think it's one area of research in machine learning that is making a lot of theoretical progress. I'm just going to touch on a couple of the key techniques. Now, this is just, if it's not clear, is about taking a machine learning model that you've built and making so that it is faster or more performant in some way. So the first is graph pruning. So graph pruning, the idea is if you inspect the weights of a neural network, there's actually a lot of sparsity. There's a lot of weights that are very close to zero. And if they were hard zero, your model probably would still work. And so there are techniques where you look for these weights and you prune your graph, and taking advantage of things from sparse matrix theory and just the fact that you already have a new graph that itself can be optimized in other ways using graph theory. You can build a new model that is essentially identical, that has substantially less model weights, has substantially fewer biases, and therefore has a substantially smaller matrix multiplies, thus making your model faster or have a lower footprint on your GPU, which means that you might be able to run inference with larger batches, which means that you have higher throughput on your service. And so there have been tools to help with graph pruning for quite some time. NVIDIA released their own tool. When did they release it? WonQ with TensorRT, like 6 years ago, 7 years ago, 6 years ago. And then now, if you're using JAX, which you should be because Uche taught you how to use it, JAX itself has all kinds of CUDA optimization techniques, including just-in-time compiling, as well as other optimizations like graph pruning. And so here's a comparison of JAX without JIT and with JIT. Quantization is another technique. If you look at like the documentation for CUDA, you'll see that you can operate modern GPUs, and this is true for, I think, TPUs too, operate them in multiple different precision modes. So you could operate within 32s, you could operate within 8s. And so the technique of quantization, and there's actually multiple related techniques in deep learning, typically means that you basically retrain a model that requires lower precision. It's kind of a less bang version of pruning in a sense, where instead of saying that it can just be 0, you say that you don't really need 32 bits of precision. You can get away with 8 bits of precision. And actually, there have been a ton of papers that actually have looked at the effects of quantization, and obviously you can build acceptable models that are very performant, and NVIDIA has continued to do more and more work to provide more hardware support for low bit precision. There have even been papers that have tried doing things with single bits and using like XOR instead of multiply. And one, they found that it actually still kind of works. And two, in some cases, they found that quantization acts as a form of regularization. It's kind of like a form of dropout. And so you can actually make your model better by quantizing it, and then you'll make everyone else happy because your model doesn't break the computer. And so, but yeah, I recommend that you look into how to either retrain your model to use quantization, or in some cases, train your model from the beginning to use lower bit precision, which also is a good technique. Weight migration. This is not like a commonly cited form of model optimization, but so if you look at a bigger picture of where your compute time is in your machine learning model, it lives as part of a bigger piece of software, including like import management and all kinds of other stuff that is needed, the call trees, the classes, everything that needs to be imported so that you can run your little bit of code. If you have a very small machine learning model, which you should aspire to do because many problems can be better solved with a small machine learning model with less data, with more reliability than with a large one, it might be the case that your model is so small that just the overhead of using all the libraries or all the support that is needed to make your model performant is more of a hindrance than the gain you get from how fast JAX is on a GPU. Or you might not have access to a GPU, or you don't want to reserve a resource just for this one little function that runs a little linear regression model. It might be the case that after you train your model, you can just inspect the model weights and pull them into NumPy or into C. And what I'm referring to when I say migration, I mean inspect your data structure, your matrices, your biases, all the parameters in your model, extract them and put them into a context that might just be a little C function, where you might just have them as constants at the beginning of a C file, or they might be just used natively in a Python function or something. And by getting rid of overhead and migrating your model from a fancy ML library to just code, you might find that it's actually faster. And the smaller the model, the more likely this is to be true. But you should aspire for small models, and therefore you should aspire to migrate your weights eventually. And by the way, I mean, one place where you can see this is if you inspect the code of top chess engines like Stockfish. So modern version of Stockfish uses a neural network for evaluation, and they train that using like TensorFlow. But you don't import TensorFlow when you're on Stockfish. Stockfish actually has a JavaScript version. What they do is they migrate the weights to a form that can run not only on the CPU, but also taking advantage of super vector operations that Intel CPUs have if they're available. And so they actually get better inference performance just using the CPU by migrating the weights out of the development system, which is just a normal ML pipeline. Student-teacher models, this is one that we use. It's very common. The idea here is that you train a fancy model and then you train another model to replicate the fancy model. It's a really good technique for things beyond optimization. Like you might not want such a big or complicated model in production. But the idea is you're using a model to train a model, and then the second model you train doesn't need to be as big as the initial model. And so that's a great technique for model compression. Embedding reuse, this is something that is very common, and to be honest, like just laziness factor drives people to do the right thing in this case, which is there are a lot of advantages to continuing to train like word embeddings along with your model, or your BERT embeddings along with your model when you fine tune. But in many cases, you're doing something where the embeddings are already good enough. And in many cases, your embeddings, and this is more and more true every day, are much, much bigger than any fine-tuning model that you have downstream. And so by freezing your embeddings, you have far fewer free parameters when you train your model, But the other performance advantage, and the one that I'm highlighting here, is that if you train 10 models that all need word embeddings, that are all doing different language tasks, if they all use the same frozen embeddings, then you actually can, and they're maybe running it on the same machine, you can save hard drive space, you can save RAM, you can save compute by just reusing those weights in a pipeline fashion. All right, model validation. This is obviously really important if you care about what you're building actually working in the real world, which is a hot topic in machine learning these days. But the basic stuff here is, so the 3 data sets: test set, training set, and validation set. Does anyone here? Yeah, I even have the answers on the wall. Want to tell me the difference between a test set and a validation set? No one wants to tell me? Does anyone know? Has anyone ever used a separate test and validation set? Cole, thank you.
Your validation set you can keep looking at and tune hyperparameters.
Yeah, so validation set allows you to tune hyperparameters, and then your test set allows you to then see what you left with at the end. To be honest, if you have many stages in building a machine learning model where you're tuning knobs and you're not allowed to cheat when you turn the knobs, every stage where you can't cheat, you need to have another form of validation set. So if you have hyperparameters and hyperparameters and your algorithm choice, eventually you should consider adding additional bits of validation every time you as a person or the machine learning algorithm had to make decisions about tuning parameters. So whether you're just randomly picking hyperparameters and doing a grid search, you need a test set to test that your hyperparameter search is actually making progress. Precision versus recall. This is if you're doing a detection problem, so detecting whether someone has cancer, detecting whether someone cursed in an NLP model, you have several types of errors. You have 2 types of errors, right? You have a false positive, where you've identified something that happened, but it didn't actually happen, and false negatives, where you were supposed to identify something happened, but you didn't identify it. And so precision, we show graphically here, is basically how many of the things that you were supposed to select did you select, and then recall is the opposite here. And so there's a lot, precision, recall, the sensitivity, precision. There are 30 names for each of these things. You should be familiar with all of them because they are used fluently in discussing model performance. You should also familiarize yourself with the F1 score, which is a hybrid of essentially precision and recall that's used to sort of split the difference, because sometimes you care about both, which we're going to talk about a little bit more when we talk about model communication. Here's the formulas for precision, recall, sensitivity, specificity, all these things. It doesn't include the F1 score, but you can also look that up. Classification accuracy versus loss. So this is a graph of a loss curve that goes down and then starts going up, and yet the validation accuracy stays the same. Does anyone have a guess why this might happen? Like, why might your classifier maintain its accuracy, but your loss actually starts to go up? Anyone? Wonkyum? Yeah, overfitting is I would say overfitting is the root cause for sure. But maybe at a higher level, there's a couple things that can actually happen. And this is from Juicy Huotari. So there's actually different situations where this can happen, but basically the predictions can get more confident, and then the loss doesn't have that much signal. So imagine, and this is related to maybe having unbalanced distributions as well. Imagine you're training a classifier, but 95% of the data is all dog, and then there's 400 other classes in the other 5% of the data. The model maybe is performing with only an accuracy of a very low number of percent, because it's maybe overfitting on small numbers of examples of birds and cats. And it's just basically the model can decide, you know what, I'm just going to say dog all the time, right? And that's going to get me a higher validation accuracy, but my loss is going to get worse, depending on what your loss function is and how you're doing that. And the model also can start to essentially overfit on the data set, and then identify patterns that are not going to extrapolate well to your validation set. And that's the reason why you have a separate validation step, so you can know when you started overfitting. Regression accuracy. So I'm only going to talk about this briefly, but when you're doing a regression problem where you're trying to predict some sort of continuous scalar, there are many different loss functions and many different forms of regression. Most commonly, you're going to have something like mean squared error. But you should, if you're going to validate your model, make sure that there aren't weird side effects of your choice of regression loss function. So for instance, maybe there's an asymmetry or skew to one type of error being worse than another, or there's a long tail in your distribution that you're trying to model with a regression model. That should impact your choice of not just loss function, but also if you're adding regularizers as well. You need to think about things like asymmetry in your data set and other things that might cause you to choose a more exotic regression loss function. If you're training a sequence model or a model that resembles a sequence model, which, like we talked about transformers and language models earlier in this series, one common way to both measure error and to measure loss is using the LEVENSHTEIN distance, which is derived from the edit distance, which you might learn in your algorithms class as a common application of dynamic programming. It's a relatively complicated loss function compared to something like mean squared error, but it is something you can make differentiable and is regularly used for both generative models like a language model, as well as other models where you might be performing a sequence-to-sequence task, like let's say translation. And so you should both know how to implement the LEVENSHTEIN distance and how to implement it as a loss function in something like JAX. All right, reliability and safety. So this is a hot topic. I only have a couple slides on it. So empirical validation. So I want to do an experiment. I need a volunteer. Okay, Nick. All right, so we're going to play a game. Everyone's going to play this guessing game, and you're going to have to be really sneaky here, Nick. Mm-hmm. So here I've got two dice here. This is a 20-sided die, and this is a 4-sided die. And the way you read it, number that's up on this one. Okay. Okay. And Nick is going to roll. I'm going to give him one of these dice actually, and Nick is going to roll it and is going to announce the number, and then he's going to do this several times. And then your guy's goal is to guess which of the dice did I give him. Okay. So you have to be really sneaky here, and no one peek. I'm going to give you one of the dice. Okay, and I want you to just keep announcing numbers as you roll the die repeatedly.
2, 4, 1, 1, 1.
Okay, that's enough. Okay. So who wants to guess? Did I give him the 20-sided die or the 4-sided die? Nico? 4. You said the 4-sided die? If I held a gun to your head, how confident would you be? If you were wrong, you die.
What units did you want that in?
I don't know. Tell me. Are you confident enough that you would do that?
Sure. Yeah.
Okay. Just from 5 dice roll.
Yes.
Were those 5 numbers possible on the other die? Is it possible that you were wrong?
Yes.
That's true. So you're right. He was rolling the 4-sided die. And so good job.
Thank you.
So that's crazy, right? Those numbers could have come out of either of those die, and yet just from 5 rolls, Nico was able to get it right, and that was with a gun held to his head. So that's called empirical validation, right? There's a lot of misinformation, even from very smart people, about machine learning models and how reliable they are. A common opinion that you'll hear from, again, very smart people is that you can't trust machine learning models because you never know what they're going to do, or because they make errors, and therefore they can't be used like normal real software where you have a procedure and the procedure is already right. And there's a little shred of truth to that. Like if you write a piece of software and you write enough tests and you test exhaustively every single test case. So like, for instance, if you were making a small microchip that just does combinational logic where every possible input and output state mapping, you can exhaustively test your device and make sure that it is always correct. But generally, I don't know if you guys have ever worked with software before. It sucks. It's always wrong. It's always broken. And errors are like, you can't prevent them from happening. Machine learning models, for better and for worse, are a form of optimization where you're optimizing often against a very simple metric. And so like software, you have to test them. They are software, right? and you need to empirically start to build confidence about whether it's going to perform. And so anyone who tells you you can't use machine learning for healthcare or for cars or whatever, some critical application, because they're just too unreliable compared to an algorithm or a procedure, one, has never written an algorithm or procedure and doesn't know that you get it wrong 100% of the time. And two, doesn't understand this like basic dice test that we just did, which is that you can empirically validate things. We build very, very complicated things that touch real world hardware that goes into space or that goes into the deep sea, where a lot of the components you can't test perfectly under the real conditions. So this is a picture of the engineering model of the lunar lander, the LEM. They tested this out at what is now Armstrong Air Force Base, and they couldn't actually go to the moon and test the real thing, right? That's really scary because they actually put a person on it the first time they sent it to the moon. And so what they did was they put a jet engine on the bottom of a fake one so that it would take off about 5/6 of the 5/6 of the gravity, I think, or most of the gravity, and basically operated like it was on the moon. And they gave it, as best they could, a emulation of how it would perform in its flight characteristics on Earth. And this actually almost killed Neil Armstrong. He ejected when one of these exploded. But he succeeded on the moon, right? And that was through empirical validation. You test something repeatedly under the closest conditions to the production conditions as you can, and you can start to build confidence. And that's true about machine learning, and that's how you build safety into machine learning, is you test them. So this is a picture of a Tesla that crashed while it was running its autopilot. So obviously errors occur in machine learning models. Most of the time, your validation loss or your validation errors are not going to be zero, right? Your model will fail sometimes. It's not going to be able to perfectly extrapolate to the real world. And that is true about all engineering systems. That's true about the engine in a car. That's true about the brakes in a car. None of them are perfectly performant. And so a common argument that you'll hear maybe from the defenders of autonomous vehicles is it doesn't have to be perfect, it just has to be better than a person, and people are really bad at driving, right? And so I don't mean to encourage you to be cavalier about deploying models in real life. In fact, that's the opposite trend or opposite thesis of most of this conversation. But you do need to be realistic, and you have to be realistic when you're talking to other people about what your actual goals are with any engineering system, whether or not it includes machine learning. And that's true with autonomous vehicles, which obviously life's on the line, really high bar for performance. But the thing is, like, there are many cases where you do not need a machine learning model to be that accurate. If you just need it to, let's say, filter some data so that you have less garbage, or get signal to noise down, or give you an eyeball, or you're going to average many outputs from your machine learning model, and so that you can beat down the error from many observations. Machine learning models can sometimes be barely more accurate than random chance and still provide value. And that's true throughout engineering, and is an important point that is not said enough in that community, which, again, most of that community has never sent anything to production, so they wouldn't know. They just are trying to optimize a number and publish it. Engineering safeguards, so specifically like detecting faults, working around faults. So one recent example is how do you prevent ChatGPT from being racist, right? You can obviously try to solve it at the model development stage, like remove racist data from the training data, but it's data from the internet, so it's like all racist, and so it's almost impossible. So you can build safeguards on top of your system, and this is true about almost all types of machine learning. You don't need the machine learning model to be your entire software. You can have other models that are designed as point-wise safeguards. You can perform empirical tests, recognize common failure nodes, and then build other detectors around them. Those are called fault detectors and fault responders. And you can integrate that into your software development process so that you can build something that you can be confident in and that has the right safeguards for things like safety and privacy. All right, the last topic is communicating about ML. How do you talk to other people, many of whom are not technical, about your machine learning model, which is something that you might be so lucky to do if your model is worthwhile. And so types of accuracy. This is a common topic that you're going to be talking about. In a multi-class model, for instance, oftentimes you'll see, like, for an image classification model, you'll see the top 3 predicted versus just the top 1 predicted versus maybe the error or the loss. When you're talking about a machine learning model's accuracy, you need to be very careful about what type of accuracy you provide. You might both undercut or present your model by choosing the wrong accuracy measure. So in the case of, again, classification models, if you have, let's say, you talk about the emotion model that Phoebe showed earlier this week, right? And let's say that you misidentify sad as upset or sad as angry. Is that as bad as misidentifying sad as elated or happy? And the answer is probably no, right? And so when you're reporting a metric about your emotion model's performance, it might make sense to be a little bit more thoughtful about actually what you report. And there's a lot of ways that you can solve this, including things like whether, maybe the number 2 was almost as high of a softmax activation as the top one. And so there might be other ways to use the model or other ways to measure its accuracy that are more correct to how it's going to be used. And then the other side of the coin is true as well. Don't choose a flattering metric to report your model that isn't realistic for how it's going to be used, because you will confuse people who are then going to be unhappy with what you give them because you didn't meet the requirements that you promised. Machine learning requirements. This is a really fraught field. All engineering systems, if they are serious engineering systems, have some requirements when you start or as you begin to define what product you're trying to build. And so this is like a diagram of a 100-year flood, right? You're engineering a dam, you engineer it for maybe a 100-year flood, the biggest flood you're going to see in 100 years. When you're designing your machine learning model, you should be designing it for your 100-year, accuracy loss or whatever. And so your 100-year mistranscription. And generally requirements about machine learning models, they need to be realistic, because there's oftentimes, especially communicating with the general public, a expectation or truism that the system must be 100% accurate or must be accurate beyond the state of the art by orders of magnitude. And you need to calmly communicate either that's not possible or is that really what you need for your use case. Because like I said, there's many safeguards you can build on top of machine learning models to make them still useful. And very few things in the world need to be 100% accurate. But that said, when you're defining your engineering requirements, you need to be conscious of things like, okay, well, if I'm running my model 10,000 times a day, and all I care about is per hour how many failures there are, you could have 5% failure rate every hour on the hour, and that could be fine. But if you concentrate all those failures in like one time of day or one case, or you have a bias in your failure modes, that could still technically have the same failure rate and still meet your engineering requirements, but no longer be a valid system. And so designing machine learning requirements requires really good understanding of statistics, like a much better understanding of statistics than the average ML practitioner, which is 0. And you also need to have a really good understanding of how those requirements are going to be understood by other parties and by stakeholders and by people buying your software. And so it's definitely a complicated process. And the rule of thumb is think about what your model is actually going to do in the worst case, and then think about whether it's going to do what the person who is using it needs it to do. And if there's a gap there, then there's probably going to be a gap in your requirements. But if there isn't, then you should define the requirements so that as you continue to change your model over time, it continues to be performant. Precision recall trade-off. I alluded to this earlier when we talked about precision and recall errors. This is a graph of a precision recall curve. And the idea here is, let's say that you have a engineering requirement that you, in your curse word detector, that the only requirement is that it has to have a false positive rate of below 5%. Okay, so that means that every time you identify something, it just can't be wrong more than 5% of the time. If you just never returned that you found any curse words, or you very rarely did, then you might trivially have a very low false positive rate because you very rarely are comfortable ever reporting any sort of identification, right? You can trade off precision and recall. You can make a system that is very, very over hesitant to ever identify something in a detection problem, or you can build a system that is very blasé about identifying everything in a detection problem and optimize precision or recall. That's why you have metrics like the F1 score, because you can trivially exchange one for the other. And that also, can allow you to cheat in ML requirements. And so you need to actually be realistic about what your precision and recall error reserves are. Comparing models, this is again another bit of flex here, but this is actually out of date. This is when you're comparing models, there are a lot of problems. So one, a lot of models might have their performance reported by the parties that trained the models, and they might have different criteria for how they evaluate their model, different data sets. And so if you want an apples to apples comparison of two models, you need to have the same data set, the same way of scoring the data set, and you need to make sure you're using the models correctly. And if you want to so these were all measured with the same data sets and the same metrics for every model, by the way. You can guess who made this graph. It was either Gridspace or Human, one of the two. Confusion matrices are really common in especially communicating about multi-class problems. They're essentially the multidimensional version of a precision recall square. And so what you essentially are showing typically in a confusion matrix is like a correlation matrix, the error between categories where the diagonals would be a true true negative, they have it labeled. But yeah, I mean, basically you correctly want to identify something as the class that it belongs to. Confusion matrices can be useful because like when we talked about like the emotion model with like maybe sad and angry are very highly correlated, and you maybe are okay with that. So if you look at the confusion matrix, you might in that case recognize specific false positives and false negatives that you're okay with because you understand them. And so confusion matrices, one, are very information dense. Two, they're often really good at diagnosing multi-class models. And they're very good about communicating to others about the model's strengths and weaknesses. And even if your model does have strengths and weaknesses, like for instance, maybe it confuses two similar classes, that might be okay. And like we talked about earlier, maybe your actual metric is the 3 best, or maybe it's okay if two classes get confused. And alternatively, it can be really good at diagnosing, like I said, like, oh, these two classes are getting confused. Clearly, it's this feature, or it's clearly this property of these two classes, or is maybe a problem in your labeling process. Error tolerance. So this is another thing when you're communicating to the outside world that is going to, depending on who you are, cause confusion, eliminate confusion, allow you to cheat, prevent you from cheating. So let's talk about, like, for instance, speech recognition, right? So let's say your word error rate is 10%, right? That's 90% accuracy. That's pretty good. Let's say you reduce it from 10% word error rate to 8%. That's great. So let's say that you are in your release notes saying, okay, we've improved our speech recognition model accuracy by 2%. And you don't specify what that 2% is. That could be relative 2%, which is really unimpressive, or absolute 2%, which is very impressive, right? And so percentage error or relative error typically is what people imagine when you say you improve something by n%. In common language, that is most often what people imagine. If you say something has been improved by 50%, typically people imagine that you've relative percentage error reduced it by 50%, not absolute error. And so you just need to make sure that, one, you communicate what type of error it is, and two, that the person you're talking to understands the difference. All right. So, Coop, do you want to go through solutions from last time?
Yeah. All right. So from a lot of talk about empirical evidence, we go into the highly subjective. But these are the answers, some suggested answers from the conversation design lecture last time. First problem was about describing two conversational turns when a given interaction suffers from 3 different types of very common errors in human-bot interactions. So when the bot asks, what is your date of birth? And somewhere in that, there is an automatic speech recognition error. Let's say the human's birthday is mistranscribed by the system as June 4th instead of June 4th. Could happen. Stranger, worse mistranscriptions have occurred. If that were the case, we'd expect a bot reply that was authored well to be something like, I'm sorry, I probably misheard you. Could you say that again? Moving on to the same situation with a natural language error, natural language understanding error. Let's say the human speaker is from the UK and uses a rare date format for their birthday, 8th of 2nd, 92. The bot could reply, I didn't understand, and then maybe append a suggestion about an ideal format, such as, I'm sorry, I didn't understand. With April 3rd, 1989 as an example, could you tell me again? And then we'd get to a place where the bot would more easily recognize the format of the answer. And then for a TTS error, which is kind of error moving the other direction, if the bot makes a goof, a bizarre glitch makes the bot's utterance date of birth sound like daybird. The human speaker wants to be sure they know what's happening, so they say, "What was that?" So that's one turn each, 2 turns that are very plausible for those for that interaction given all those errors. And then finally, in the enrollment process for a new customer, the virtual agent must ask 10 mandatory questions. Very, very common to have this kind of survey or onboarding biographical test applied in conversations such as this, by the way. We would write signposting dialogue for the virtual agent, which aims to prepare the customer for this part of the conversation. And I've written, the bot would say, next I have 10 questions to ask you. So there's the scope of the task. We can't skip any of them. There's the requirement. So no, really no room to object there other than hanging up the call. But they're not difficult. So put people at ease. And then it should only take a minute or 2. And contained within all of that answer, the human caller should be perfectly well prepared for the unskippable questions that they have to ask and hopefully not get upset at the bot or at the organization the bot represents. So a lot of leeway in all these answers, but if you did these exercises and you came somewhere close, good for you. And if your answer is very widely from mine, figure out how to contact me. I'd love to have a healthy debate about it. Now back to Anthony.
All right. Well, here are the final exercises. We'll never give you the answers because it's the last lectures, but what might be a good monitoring metric to autoscale a speech synthesis microservice? So another way of saying that is you have to generate lots of speech synthesis, maybe with different amounts of load. What should you measure to figure out how many you should run? A speech recognition model has a word error rate of 9%. You have a downstream curse word detector. How might you achieve a target false positive rate of 5%? And then the last exercise, which is required, is share Gridspace IAP with a friend or colleague. Reach out to us and give us any feedback. So let's wrap things up. That's, I get through everything. There we are. So continue to engage with us at iap.gridspace.com, or you can send us an email. We will continue to monitor iap.gridspace.com, especially if we do this again next year. Let us know if there's anything you liked or perhaps want future content to cover. You can also, we've been posting these to YouTube, and so you can go to youtube.com/Gridspace Incorporated. You can also follow us on LinkedIn and Twitter. We've covered a lot of stuff. We went through the fundamentals of sound and signal processing, machine learning with JAX. We did a simultaneous coverage of linguistics and NLP. We went through the pillars of speech technology, speech to text, text to speech, and dialogue systems. And then we covered the real world, which is very rarely covered, I think, in these contexts, where we talked about emotion, dialogue acts, personality, lying, ethics, conversation design, and then deploying things in the real world. And so we covered a lot of stuff. We'll have all this stuff on YouTube. Hopefully you guys find that useful. If you want to do this for your job or you want to intern with us, we're going to be recruiting at MIT on February 10th at the X Fair. We're going to be recruiting at Stanford on March 2nd. We're going to be doing some LA office visits for recruits in spring 2023. And you can always reach us at hiring@gridspace.com. And I just wanted to say thanks. So thanks, everybody.